So welcome everybody. We're going to start the linear algebra module today. And I'm pretty excited for a number of reasons. One of them is that we haven't received any negative anonymous comments in a whole week. So maybe, I don't know, could mean nothing. But we're encouraged. Second, because linear algebra is a really beautiful subject, and hopefully we'll transmit some of that to you. Some of you are probably confused or a little worried about the dates of the exercise sets and the test for the programming module. So we've purposely kept the exercise set for this week. We've made it relatively short. Should be relatively easy to do. We think it should take about 1 lab's worth of time, not 2 labs. And if you look at it, you'll see that it's wordy. It's got a lot of explanations, so it looks long, but it's not really that long. At least that's the intent. And to give you guys flexibility, it's not going to be due until a week from Friday. So that is after the programming module test is due. The programming module test is due at the end of Monday. It'll be out on Friday, and it'll be due at the end of Monday. Now, that being said, we're recommending that you hand it in this Friday before you get the programming module test, because we don't want you guys to just be focusing on the module test and not learn anything today or the next lecture. So we're hoping that you guys will do that, and we'll go through that, and we'll absorb some of the material. Once again, we're trying to keep it short so that it's relatively balanced for you. One person asked how long we expect the module test to take. We're still putting the finishing touches on it. We're thinking that if it's hard, it should take maybe 3 to 4 hours if it's really hard. And if it's easy for you, there's going to be some people for whom it's easy, some people for whom it's hard. And if it's easy, it should take about an hour. We're not looking to make you work for hours and hours and hours, just to kind of like do a little test. So that's the goal. Yes?
So if we use anything on the internet, we have to sign.
Oh, yes, thank you. Great question. And we should probably announce this on Blackboard or something. Yes. The only thing you're not allowed to do is to collaborate with other people, so your work should be your own. But other than that, you can Google, you can look at past notes, you can look at the recordings from the lectures, you can do whatever you want.
You don't need to cite.
Say it again? Oh, yeah. And if you Google or look something up on Wikipedia, we don't need the citation. It's totally fair to just go and use it for your own purposes. Thank you. Okay. The last reason why I'm a little excited or perhaps nervous today is because I'm going to try a little bit of an experiment. I know you guys like to have the notes beforehand, and I know you guys like the lectures recorded. And this lecture was going to be a Blackboard lecture, and the recording when it's a Blackboard lecture is a little bit of a pain. You can't see it that well. So I thought, wouldn't it be better if it's something that's on the screen? And that also allows me to produce notes, so I'll be able to send you guys all the notes from what we did in lecture today. So I got this new toy just for the purpose of this class, which is this tablet here. And so the idea is that it'll be like a Blackboard lecture, but I'll do it on this, and all the files that I get produced from that, we're going to post them, and you guys will have the notes. So as in previous classes, there's really no need for you guys to have your laptops open. You can close them. You'll get a copy of everything. So hopefully you'll be following along. All right. That said, let's start with linear algebra. And I'm going to start with something pretty simple. I'm going to start talking about how we represent things, what the language that we use to represent these. And in linear algebra, these are called bases. And imagine, here's a simple example. Imagine that you're looking at the height of a person. You're talking about the height of a person. Okay? And I might tell you that this person happens to be 1.8144 meters tall, for example. And now I ask you, how many inches is this person? How tall is this person in inches? You have to kind of stop and think for a little bit. Right? But say I could equally well tell you, oh, this person is exactly 6 feet tall. And then if I ask you how many inches tall are they, it's a little easier. Or even further, I could say, oh, this person is 72 inches tall. One of the experiments is whether you'll be able to read the handwriting. As you can see, it doesn't come out that great. So please tell me if you can't read it, because then I might have to default back to the blackboard. So clearly, if I'm asking you how many inches tall is this person, if we wrote their height like this, it's really easy to answer, right? Conversely, if I'm asking you how many meters tall is this person, if we wrote it like this, it's really easy to answer. So depending on what question you're asking, how you write the very same information can be really easy or really difficult to answer. How you represent information has a huge effect on how easy or how hard it is to compute with that information. And that applies to this simple example. It applies to your brains. Re-representing information in a way that makes it easy to compute with it, that is a super huge theme in what we're going to be talking about. In fact, that is the story of our linear algebra model. Re-representing things in a way that makes it easy to compute. So if we look at this and think a little bit about what we're doing, when we said that the person was 1.8144 meters tall, we're comparing to, let's say that were a 1 meter tall yardstick, right? So what did we mean? What we meant is that if you take this yardstick, you have to go this long times 1.8144 of it to get to the height of the person, right? That's what we mean when we say 1.8144 meters. Take a meter yardstick, multiply it by this number, 1.8144, to get to the total height. And the same thing when we were talking about the height of this person in feet, and the very same thing when we were talking about the height of this person in inches. These things, these units, those are going to be the bases that we're going to be talking about in linear algebra. And here, we're just talking about height, so we're just talking about one dimension. There's just one number that we're representing. So it's relatively simple to go back and forth between the different bases. The bases are the framework, the units that you're using to describe the information. In linear algebra, we're going to be doing this, but not just for one dimension, but for many dimensions at once. And so that means that it gets more complicated. It also gets a lot more powerful in the sense that the operations that get easy in certain representations are some really amazingly difficult operations that when you see them, you'll be amazed that you can do them. So it's powerful in the sense that it lets you do a lot of things that you couldn't do before. And it's also really beautiful. I hope that we'll be able to transmit some of that beauty to you. I don't know if we will, but certainly we'd like to try. Okay, so this was an example of using different bases, different ways of describing the same information in just one dimension. And I want to point out, I want to really emphasize that when we change from this description, from meters to feet to inches, we're not changing anything about that person's height, right? The person's height is something that exists independently of the language that we're using to talk about. That is also going to apply in linear algebra. Most of the concepts in linear algebra have a geometric interpretation that exists independently of how we describe these various objects. And what you see is that both vectors and matrices have a geometric interpretation. And understanding what that underlying geometric meaning is, that gives you a huge amount of insight and intuition and lets you work much more efficiently. Okay, so the height is something that exists independently. Here it was just one dimension. Let's do it for more dimensions. So let's imagine that we're looking at a vector, and when we were looking at vectors in Julia, just thinking of programming, we were just thinking of them as lists of numbers. Okay? And here what we're going to do is think of them as dimensions, not just lists of numbers. So let's imagine that we're looking at a space, and we're going to look at a vector. Here we're going to look at 2 dimensions, because of course 2 dimensions is easy to do on the board. But generally what we're going to be doing will apply to higher dimensions also. It will apply to n dimensions in general. And let's suppose that we're looking at a vector, which is this one, 3, 3. So it has 2 elements, 2 dimensions, and both of them happen to be the same. So you guys have done this kind of thing before. You plot it out in Cartesian coordinates. Here's 1, 2, 3 horizontally, 1, 2, 3 vertically, and here we are. So what is it that we're doing when we write out these dimensions in Cartesian coordinates? What we mean is that this vector x, this list of numbers, is a position in space. It's this point right here. Right? We can interpret it as a position in space. And how we describe that position in space is by saying, how do you get there starting from the origin? So how do you get there starting from the origin? You walk 3 steps along the horizontal axis, that's the first number, and then you walk 3 steps along the vertical axis. Right? That's the second number. That's the standard thing that, that you guys have been doing in school. So let's describe these axes a little bit more. Right? Often, we just think of them as, oh, they're the implicit axes. But we could make this a little bit more explicit by saying, well, here's a vector that lies along the direction of the horizontal axis. We're going to call this guy I hat, okay, with this kind of triangular hat. That triangular hat means a vector of length 1. That's going to be our convention. So let's have 2 vectors representing our 2 axes, the vertical and the horizontal axis. And the vertical one we're going to call j hat, and the horizontal one we're going to call I hat. So now this vector x equals 3, 3, what we mean is take, go 3 multiples of I hat, right? So we can also write it as 3 times I hat plus 3 times j hat. Right? And that's what we meant when we wrote it here. Is this, I hope it's legible. Nobody is screaming at me that it's not, so I'm assuming that it more or less is. So this 3, 3, what it really meant, this number was how far to go along I hat, and this number meant how far to go along j hat. And the default is, if we don't specify anything about our axes, if we don't say there's anything special about them, is, oh, we're using the standard Cartesian horizontal and vertical axis. But we needn't have used these particular axes. We needn't necessarily have used this particular I hat and this particular j hat. For example, let's suppose that I'm going to have to let you guys know, this is also, I only started playing with the software yesterday, so I'm not completely familiar with it. But let's now describe some other axes. So let's say that now we're going to have a vector j hat that is 2 long, that's 2 units long. Okay? So this is a new j hat in blue. And let's say that our blue I hat stays the, oh, that came out terrible, that our blue I hat stays the same as the original. Okay? So now we have a new I hat and a new j hat. And we want to, again, describe this point x, in terms of how far do we have to move along the blue I hat, and how far do we have to move along, along the blue j hat. And in this case, x, how many multiples of the blue I hat should we move to get to the point x? 3, right? So this would be 3 times the blue I hat. And how many multiples of the new blue j hat do we need to move along in order to get to x? Somebody said 1. I tried to make this arrow too long. We need to get to 3. So it's 1.5. A lot of people said 1.5. So it's 1.5 j hat. Right? So in the blue coordinates, the same point is 3, 1.5. And what you can see is that this is exactly what we did when we changed from meters to feet to inches, right? We're changing the length of our yardstick. And in this case, we changed only one. We changed only the length of j. So it was only this one that changed. And what we're being explicit about by writing out which axes we're using, these unit vectors, when we write it out like this, we're being explicit about what units we're using. Instead of just saying 3, 3, we're saying 3 what? inches, meters, feet, pointing in which direction. So just like we did that, we could do the same. We could have some new coordinates, but they don't necessarily have to point in the same direction as the original I hat and the original j hat. Right? So the first thing that we did when we went from black to blue was change the length of one of them. Exactly like going from meters to feet. Right? In this case, we changed the length by a factor of 2. Now let's also change their direction. Let's say that the vectors that we're going to use to describe this point x, let's say that they were these guys. Okay, so I've got a new I hat and a new j hat. And in this case, I hat, if I were to describe it in the original coordinates, I'm going to make it length 1. I'm going to keep it length 1. And in the original coordinates, it's going to lie along the 45-degree line. So it's going to be 1 over root 2, 1 over root 2. Those are its coordinates in the black axis. So how long is this red I hat? What's the length of this vector? How do we find the length of a line? So if you have a line and you know its horizontal component, how long this horizontal component is, and you know how long this vertical component is, how long is that line? Let's say that we're going to call this part, we're going to call the horizontal component A, and we're going to call the horizontal component B, and let's say that the length of line is C. And I didn't put this in the little reminder file that I sent out last night, but most of you guys know this. Tell me the answer. How long is C? Yes, a squared plus b squared equals c squared. Pythagoras' theorem. So c squared is the square root of a squared plus b squared. Okay, so how long is I hat, this I hat right here? If its horizontal component is 1 over root 2 and its vertical component is 1 over root 2, how long is it? So here, 1 over root 2 corresponds to a. That's, remember, the first number. If we're using our regular Cartesian coordinates, this is how much you move along the horizontal, how much you move along the vertical. So 1 over root 2 is playing the role of a. And this other 1 over root 2, also 1 over root 2, is playing the role of b. So how long is c? So we square a. If we square a, how much do we get? What is 1 over 2? And if we square b, how much do we get? And if we add the 2? And what's the square root of 1? 1. Yeah, right? I was promising you that this was a vector of length 1, so here, it's good to check that if somebody tells you there's a vector of length 1, how do you check it? You square each of its elements, and you add them all up, and if they all add to 1, then it's a vector of length 1. Okay, so this I hat is a vector of length 1. And I'm going to make my new j hat also a vector of length 1. But it's going to be pointing in the direction that you see on the screen. So let's see, horizontally, does j hat, this new red j hat, does it move in the positive direction or the negative direction? Negative direction, right? Because it's going leftward. So I'm going to make this minus 1 over root 2. And vertically, it's moving in the positive direction. I'm going to make it 1 over root 2. So how long is j hat? How long is j hat? You. Yeah, it's 1, right? Because if we square the first element, you get 1/2. You square the second element, you get 1/2. You add them, you get 1. Okay, now let's try to write x in these coordinates. How many multiples of the red I hat do we have to move in order to get to x? So this is length 1. We want to multiply this enough times that we get to here, to 3, 3. Any guesses? 1 over root 2 times the red I hat? 3 I hat. 3 I hat is a good guess. It turns out that the vector x, the vector I hat is length 1. The vector x, how long is the vector x? So remember Pythagoras' theorem? You square each one, you add them up. What do we get? The square root of 18. That's the square root of 2 times the square root of 9. The square root of 9 is 3. So the length of x is the square root of 2 times 3. The length of I is 1. The length of x is the square root of 2 times 3. So if we move the square root of 2 times 3 along the red I hat, then we're going to get. So we need to move 3 times the square root of 2 times the red I hat. And how much do we move along the red j hat? What do you think? 0. 0, right? Because the red I hat is already pointing right at x. We don't need anything more. So in these red coordinates, the same vector x, the very same guy, is now 3 root 2, comma 0. That thing is a 0. Here, let me do the 0 again. Just because it looked. Well, I don't know that it came out better, but anyway, it's a 0. And the point that I'm trying to make is that you can choose your axes however you like. The same way that we could choose to describe the height of a person in meters or feet or inches. And some of those choices are going to make some things really easy to figure out, and some of those choices are going to make some things really hard to figure out. So we want to find the choices that make things easy to figure out. There's many different choices that you can make. And linear algebra has like 3,000 million different ways to choose bases for this or that or the other. We're going to look at just one of them. We're going to look at the most important one, the one that is the most powerful. It's not the one that solves every problem, but it's the one that solves a lot of problems, and that's why it's the one that we're going to focus on here. Okay. So as we've been going through this, as we've been going through these examples, we've been doing a couple of things that I wasn't stopping to define. I was just kind of using it, which is we said that a vector was a point in space, but we didn't really specify how do we multiply a vector times a number? How do we multiply a vector times a scalar? What does that mean? Or what does it mean when you add two vectors together? We just kind of did it intuitively. Let me go through that. I think those two things are reasonably straightforward, so that should be relatively easy. So the first is multiplication by a scalar. Say that we've got a vector, or actually before I say that, I want to point out that when we think about these things, when we think about some operation with a vector, something that we do to it, there's two ways to think about it. There's the, what do you do to the numbers that describe a vector? You've got a vector in Julia, you do something to it, what happened to those numbers? And I call that the numeric interpretation, or the numeric operation. And then there's also a geometric interpretation. Geometrically, what does it mean? What happens to a vector? And there's a one-to-one relationship between those two. So on the one hand, we have the numeric action, and on the other hand, we have the geometric action. So let's do multiplication by a scalar. Let's say that we have a vector x, and let's say that we're going to multiply it by a scalar. When I say scalar, I mean a single number, not multiply it by another vector, just multiply it by a number like 3 or pi or 2.3 or anything like that. So we want to find alpha times x. And what we mean by that is that we take the vector x and we find another vector that points in exactly the same direction, but is now alpha times as long as x was. We stretch x by a factor alpha. That's what, geometrically, that's why multiplying by a scalar means. So if this was the length of x, let me see if I can draw it better than that. So it's these two vertical bars. If you have two vertical bars like that, that means the length of the vector. And another way of saying that is the square root of the sum of the squared elements, just as we were doing. So if the length of x is that, what we want to do is find another vector. The alpha x vector is going to point in exactly the same direction. A little bit of a curve. It's going to point in exactly the same direction. But now it is going to have length alpha x. Okay? So that's the geometric interpretation. That's what it means to multiply a scalar times a vector. And say when we wrote 3 times I hat, oh, that means that you move 3 steps along the I hat direction. That's exactly what we were doing, right? It was like saying, take I hat, and then you stretch it by a factor of 3. Numerically, there's something else that is happening, although the two are, have a one-to-one relationship to each other. Say that you've got your vector x, and this time I'm going to write it like this. So I'm writing a 2-dimensional vector, but it could be anything. I'm writing it in a column. That's going to be our default. And that's the default in Julia, and it's also the default in linear algebra. If we don't specify whether the vector is a row or a column, we're going to mean it's a column. And so this is a vector with 2 elements. They could be anything. We're going to call them x1 and x2. And now if we multiply that vector by a scalar alpha, what we get is just the element by element multiplication. So on the left side, we have numerically, what do you do? If you've got your numbers in your computer, you want to multiply your vector by alpha, what happens? And on the right side, we have geometrically, what does that mean? So multiplying by a scalar, relatively straightforward. If you type this into Julia, this is what's going to happen. Let's do another one. Let's do it. Any questions at any point? Always remember to stop me if you have any questions. You never hesitate. So let's do addition of 2 vectors. Oops. Oh, yeah, that's what I want. Let's do addition of 2 vectors, and I'm getting my layers all confused. Oh, yeah. Now let's do addition of 2 vectors. Let's say that we've got 2 vectors, x and y. And let's say that this is vector x. And we're going to have another vector y. And if we want to add them, what we're going to do is the vector y, instead of starting from the origin, we're going to start it from wherever x left off. So this second arrow represents the vector y, and the sum of them is going to be where you get to if first you move along the vector x, and then starting from the tip of x, starting from the point that you got to, then you move along the vector y. That's the geometric interpretation. Or geometrically, that's what we mean when we add 2 vectors. Numerically, what does that correspond to? Numerically, what that corresponds to is that if you have, say, a vector x, and I should say that what we're talking about generalizes to multiple dimensions, not just 2, and you add a vector y, then adding them simply means element by element addition. So the first element of the result is a vector, right? This thing in the thick. And the first element of it, its first coordinate is x1 plus y1, and its second coordinate is x2 plus y2. And once again, when we were describing a vector in terms of the bases, and we were saying things like 3 times I hat plus 3 times j hat, this is what we were doing, right? 3 times I hat plus 3 times j hat meant walk 3 along I hat, and wherever you get to, then walk 3 along j hat. Exactly the operation that we're sketching out here. Okay, so we've defined multiplication by a scalar. We've defined multiplication we've defined addition of 2 vectors. Now we might start thinking about multiplication. I should say that as I'm going through these things, I'm not really motivating too much about why we're doing them yet. So I'm going to ask you to kind of bear with me. We're going to get to some really nice things, but it's going to take us 2 weeks to get there. And really, the third week is going to be practicing with it. So bear with me as we go along. And I do want to mention the fact that when you think about neurons, you're thinking about many neurons at once. You're thinking about many variables at once. This is the language. This is the bread and butter language for talking about the activity of many neurons at once. So all of this is going to be very useful to you. Okay, so multiplication of two vectors. How do we multiply two vectors? Well, you can think of multiplication or addition or multiplication by a scalar as functions that you're writing and you're defining. This means that, in a sense, you're free to define what the symbol plus means or what the symbol times means when you're talking about vectors. Right? And the definitions that I just gave you for multiplying by a scalar or adding two vectors are kind of like the standard definitions in the field. But you can do anything. And when it comes to multiplication, you're free to define it. Right? You're going to define what it means. And it turns out that there are multiple definitions. There are different definitions, and the different definitions have different uses. Some are useful for one thing, some are useful for another. There's a cross product that is used a lot in physics. We're not going to use that right now. We're going to use another one. We're going to use something that is used a lot, and this one is called the dot product. And the dot product is something that you can do to two vectors to multiply them. So imagine that you've got two vectors. I don't know what, let's call this x. Let's call this vector y. And there's some angle between them that we're going to call theta. And for some reason at this time I decided to put little arrowheads on my Cartesian axes, and that's just going to confuse you, so let me get rid of them. So the dot product of these two vectors, we're going to define it in the following way. We're going to write it like this. We're going to write it as x apostrophe times y, and that means the dot product. And it commutes, meaning that it doesn't matter which one you put on which side. We could just as easily have written it as y prime times x. And we're going to define it as, what we mean when we write that is the length of x times the length of y times the cosine of the angle between them. And that's why I sent out that thing last night about definition of sine and cosine to remind you guys about that. So with that definition, let's think about some of the things that it might give us. The most important thing it gives you is a relationship between vectors and the angle between them. When you're talking about different pieces of data, for example, you're talking about the activity in this layer of network, in layer 5 of V1, and you want to compare it to the activity in layer 2 of V1, you might be interested in how parallel are those two, how similar are those two, the two vectors that represent that activity. The angle between them is a great measure of their similarity. So thinking about angles between vectors is something that you end up doing a lot. So let's think, for example, about what we would get if we did the dot product of x with itself. So if we're thinking about two copies of x, and we're going to do the dot product of x with itself. And let's follow the definition that we had here. Okay? So in other words, instead of x and y, we've got, instead of y, we're going to have a second copy of x. So what will this be equal to? If I just follow the terms here, what do I get? Well, I've got the length of x. And what should I write for the length of y? I don't think I've ever picked on you. So the dot product of x times y is the length of the first one times the length of the second one times the cosine of the angle between them. So if now I ask you for the dot product between x and itself, Say that again?
The 1 of x squared.
Yeah, because you get the length of the first one, that's the length of x, times the length of the second one. In this case, the second one is x again, so you're going to get the length of x again, so you're going to get the length of x squared, times the cosine of the angle between them. How much is the angle between them? How much is the angle between x and itself? 0. So what's the cosine of 0? 1. Exactly, right? So in this case, cosine of 0, and exactly as you said, the net result is the length of x squared. So the dot product of a vector with itself is kind of one way to ask how long is it. Take the dot product with itself, you get the length squared. You take the square root of that, you take the length. Now suppose that we've got another vector. This one I'm going to call it z. And let's say that z is at 90 degrees with respect to x. This was supposed to be a little right angle. So how much is the dot product of x with z? So let's write it out. So once again, we follow the definition. So x dot z is equal to, who can I pick on? Oh, you moved your sweater and that drew my eye, so I'm picking on you. So yeah, so here we've got the definition of what the dot product of two vectors is, and the two vectors that we're considering right now are x and z. The only thing that I've told you new about z is that it's at right angles with respect to x. Take me through it.
So it's cosine of 90 is 0, so it's 0.
Exactly. Okay, you jumped right to the end, which was great. If we had stepped through it, I would have said, oh, it's the length of x, because that's the length of the first one, times the length of z, because that's the length of the second one, times the cosine of the angle between them. Cosine of 90 degrees is 0, so this whole thing is a big fat 0. So here's another really useful thing that the dot product lets you do. If you take the dot product of two vectors and the answer is 0, that tells you that they're at right angles to each other. And that can be a super useful thing to know. For example, in motor control, some of the kind of trendy hypotheses right now, you can plan a movement, yet not execute it. Suppose I tell you, you're going to reach out and touch this button, but don't do it until I tell you. Okay? You plan it, and when you plan it, it turns out that the activity of neurons in your motor cortex, they change. The fact that you're planning changes their activity, and they seem to go to a set point that is encoding the motion that you're going to do. But somehow, even though they're active and they're in the configuration necessary to do that motion, you don't move until the go signal comes. So why is it that motor cortex is active in the same way that it would be to drive your muscles, yet the muscles don't move? So that's an open question in neuroscience, but one of the trendy hypotheses to what's going on is that the weights that go from motor cortex to the muscles, that weight is at 90 degrees with respect to the vector of the preparation activity. So the idea is that it's two vectors that are at 90 degrees to each other. If they're at 90 degrees to each other, then that gets 0, and that means no effect on the muscles. So thinking of dot products in this way, this is something that's kind of like a central and active part of neuroscience research right now. Okay, so important things for knowing about a dot product: vector with itself, its length, vector with another vector that's at 90 degrees gives you 0, because the cosine of 90 is 0. But how do you actually compute the dot product? Well, it turns out that kind of magically, there's an easy way to compute it. And this is the numeric side of things, right? What I've just been telling you for the dot product was the geometric side of things. It's the angle between the vectors, their lengths, the product of those things. Now, the numeric side of things is that if you compute the dot product of two vectors, in practice what you do is the following. say you've got vector x and vector y. You want the dot product. And notice that I'm writing it with this apostrophe. You guys might remember that in Julia, the apostrophe, and in linear algebra 2, that means transpose. If you have a column vector, turn it into a row, or flip the rows and the columns. And I also told you that our vectors, by default, are column vectors. So what we're doing here is saying turn x into a row vector. Turn it from a column vector into a row vector. And then multiply it by 1. And so I'm going to write it like this. x1, x2, there's the row vector, times y1, y2. And in Julia, and in linear algebra, if you do this, if you multiply a row vector times a column vector, like this, what you're going to get is x1 times y1, plus x2 times y2. And if we generalize to higher dimensions, not just 2, what we're saying is that you sum the product of the element by element multiplication. That's the actual operation that happens. And it turns out, amazingly and beautifully and very conveniently, that this operation is exactly equivalent to the length of x times the length of y times the cosine of the angle between them. So if you've got two vectors and you want to find the cosine of the angle between them, and you've got the numbers that represent the two vectors, this is easy to do. Right? Julia will do it for you. And finding their length is also easy. So now you take the dot product of the two vectors, divide by the two lengths, and that tells you the cosine of the angle between them. If you want to find the angle between the two vectors, you use the dot product to do it. Yeah?
Why do you transpose x to that?
So, to write this, once I've written it here in terms of the elements, I've kind of done away with row vectors and column vectors. Right? So we're doing that because the convention is that the dot product, you write it like this. This is going to generalize to how we multiply a matrix times a vector. So it's convenient. Right now, I'm just saying it's a convention. Okay? If in Julia you try to write the product of two column vectors, you do not get this. To get this particular operation, the convention is first guy has to be a row vector, the second guy has to be a column vector. And notice that the two of them have to be the same length, because otherwise you don't get the same length. There's going to be some missing elements in this sum. Okay, so very convenient way to write this, and this way of doing a dot product is super important. So, and I really want you guys to kind of have it in your heads, because when we're going to get to matrices times a vector in about 20 minutes, and it's going to be really useful if this is kind of floating around somewhere in your heads. So I made a little animation in the hope that this would help kind of like stash it into your brain. So here's two vectors. They're 3 elements long. First comes the row vector, then comes the column vector. And notice that they're both the same length. And multiplying them here, what it means is we're going to take this vector and we're going to put it horizontally with the first vector. We do the element by element multiplication, and then we sum it all up, and the sum of that is the result. Moving things always catch your brain, right? So I'm just trying to push it into your heads. Let's do that again. Element by element multiplication, then you sum it all up. That's the result, and that's the dot product. I don't need to do that movie again, do I? Okay, I hope that it's in your heads. Okay, so how come the geometric definition and the numeric definition match? It's kind of a weird thing, right? So what I told you is that x, the length of x times the length of y times the cosine of the angle between them is the same as the sum of the elements by element multiplication. So you could take that just as a given. And in fact, I'm not going to prove it entirely. I'm just going to prove half of it. But it didn't have to be that way, right? And the part that I'm not going to prove is that it turns out that the dot product is distributed. What do I mean by that? I mean that if we multiply x as a row, I've taken the transform, times the sum of two vectors, this is the same as x dot y plus x dot z. Okay. This thing is supposed to be a dot. And that fact alone, this fact you can prove from the geometry. It's a little bit of a pain to prove, so we're not going to do that. But this is what makes these two things match up. So for example, let's say that we take a vector x and a vector y, and we take the dot product of those two. And let's write them the way we were writing, explicitly writing out the bases. So I'm going to say that the vector x is a vector with two elements, x1 times x2. And by convention, I hat and j hat are a unit vector along the horizontal axis and a unit vector along the vertical axis. And we're doing the dot product of that with y. And y1 and y is itself described as how much you move along the I hat vector and how much you move along the j hat. Because of this distributive property, we can split out that multiplication. Can you guys read that? The handwriting is not too incomprehensible. More or less? Okay, that's great, because then it means that we can keep using the toy, which is kind of fun. Okay, so let's just spread it out just like you would any old multiplication. And what you get is that this is equal to x1, y1, sorry, x1, y1 times I hat dot I hat. So that was this term times this term. And now we're going to do this term times that term. So we get plus x2 y1 j hat dot I hat plus, now we do this one times that one, x1 y2 I hat dot j hat, and finally x2 y2 I hat, oh, sorry, j hat dot j hat. Now, what's the dot product of a vector with itself? You guys remember? Tell me. So somewhere back, you can always go back to the definition, right? If you forget something, look at the definition again and go through it, right? So the definition was length of vector 1 times length of vector 2 times cosine of the angle between. So the dot product with itself would be 0. So the angle between them is 0, so cosine of 0 is going to be 1. And it's the length of the first vector and the length of the second vector and the cosine of the angle between them. In this case, the two vectors are the same. Let's call it I hat, for example. Yeah, the length of the dot product of a vector with itself is its length squared. How long is I hat by convention? We said that when we put the hat, that means that the vector is length 1. So I hat dot I hat, how much is that? 1. Okay, so that's cool. I hat dot I hat, that's 1. So that means, we can just get rid of it because multiplying by 1, that just gives you the same thing back. And the same thing is going to happen for j hat times j hat, right? That's another length 1 vector dotted with itself. So j hat times j hat, that also goes there. How about I hat dot j hat? What's the angle between those two vectors? Right? So remember, when we were looking at our vectors, when we were drawing them, we were drawing I hat kind of like this. Right? That was the horizontal axis, and this guy was j hat. So what's the angle between them? 90 degrees. So if we take the dot product of two vectors that are 90 degrees with each other, what do we get? 0, exactly. So that means that this thing, j dot I hat, that's 0, so this term goes away. And I hat dot j, that's 0, so this term goes away. So the only thing that we're left with is x1, y1 plus x2, y2. And here we did it for 2 dimensions, but I hope you can see how that generalizes to any number of dimensions. Okay. So that's how these two definitions, on the left we've got the geometric one, and on the right we've got the numeric one. That's how come those two are the same. So this is incredibly convenient. Say that somebody comes along and gives you 2 vectors where each vector has 100 elements, and you need to know the angle between them. You know, if our vectors are length 2, it's easy enough, right? We plot them, we could kind of visualize it. But if they're length 100, or let's say that you're looking at activity in a cortical region, they're length 1,000,000. How do you find out the angle between them? I don't know. What you can do is, this is easy to do, and it gives you a lot of information about the angle between them. If you just want the cosine of the angle between them, remember to divide by the 2 lengths. Okay? And then you take the inverse of the cosine, and you get the angle. Okay, so super useful thing. So let's do one final example. And you guys will remember that we started with a vector at 3, 3. And then we wanted to go onto these new coordinates. We wanted to describe it in terms of this I hat and j hat, where I hat was 1 over root 2, 1 over root 2, and j hat was minus 1 over root 2, 1 over root 2. And if we want to ask how much of x goes onto I hat, what we're asking about is something that's called the projection of x onto a vector. And when we talk about the projection of a vector onto another vector, what we're talking about is, say that this is our vector x, and this is our vector I hat. What we're asking is, how much does x make you walk along the direction of I hat? And that's the same as asking, what is this distance? How do we find that distance? If we know the length of x, and we know the angle between them, how much is the horizontal distance? So this is that little PDF of the trigonometry. This is where it's coming in again. So we've got this vector, its length x, this angle is theta. How much is this horizontal distance? Anybody remember? How many of you guys actually got a chance to look at the little trigonometry cheat sheet? Nobody? Okay, let's look at the trigonometry cheat sheet. And I would say that you definitely want to know this. So, we can review it, but this is kind of like high school stuff that you're supposed to already know. So if you've forgotten it, which I totally understand, take a moment to look at it again and remind yourself so. If you have a circle of radius 1, and you're looking at a line along that circle, or sorry, you're looking at a line from the origin to the edge of that circle, that makes an angle theta with respect to the horizontal. the horizontal coordinate of this point is the cosine of theta. That's what defines the cosine of that angle. And the vertical coordinate, that's the sine of theta. That defines the sine of that angle. So, for example, from this, you can see what's the cosine of 0. If the angle is 0, so if this line is at 0 degrees with respect to the horizontal, so it's lying right here, how much would the horizontal distance be? Remember that this is length 1. 1, exactly. And what if theta is 90 degrees? Then it would be 0, right? So these are the definitions that give you those properties that we were using when we were saying, oh, cosine of 0 is 0, cosine of 90 is 1, sine of 0 is 0, sine of 90 is 1, cosine of 180 is minus 1, because then we'd be pointing back here. Okay? So now let's go back to what we had over here. So this is exactly the same problem, right? Except that now we're saying this length isn't 1, it's length x. Oh, and I guess I should have written it with this vertical bars just to emphasize that it's a length. Okay. For those of you assiduously taking notes when I do something, I'm going to remind you that you guys are going to get copies of all of this. All right. So if this were length 1, if x is length 1, what's this horizontal distance? The cosine of theta. And if instead of being length 1, it's length 10, how much would this distance be? Yeah, it would be 10 times the cosine of theta. So this distance is the length of the vector times the cosine of theta. If this vector is length 1, this distance is the dot product between x and I hat, right? Because the dot product was this length times the cosine of the angle between them. So the dot product also tells you the projection of a vector onto a particular direction. How much do you walk along that direction when you're following that vector? And say, when we said, oh, the activity in motor cortex is at 90 degrees with respect to the muscle weights when you're preparing an action but not yet executing it, what we mean, or another way of phrasing it, is that the projection of the vector representing the activity onto the muscles is 0, has 0 length. When we were looking at this vector 3, 3, if we want to find the projection onto I hat, how much is that? Well, that would be, let's do the dot product of x times I hat. How do we compute the dot product? Well, we can use either the geometric interpretation or the numeric interpretation. So let's use the numeric interpretation. And I want to remind you guys, the numeric interpretation was you do the element by element multiplication. So that would be the dot product of x with I hat would be the first element of x times the first element of I hat. How much is that? You guys are all getting too bored. Thank you. 0? No. Good try, but no. So what I'm looking for is the definition that said we're going to do the sum over the elements of the product of each of the elements. So that was that little animation. And so here are two vectors. Our x, we've got it here, 3.3. And then I hat, I wrote it up on the top left. Let me write it out again, is 1 over root 2, 1 over root 2. So I want to do x times I hat the same way that we did in the animation. So that would mean this number times this number. How much is that? 3 over root 2. And how about the second one? So this one times that one. Same, 3 over root 2. So what do we get? We get 3 times 2 over root 2. How much is 2 over root 2? Root 2 times root 2 is 2. So 2 over root 2 is root 2. Okay, maybe too many roots. but this is 3 times root 2. And that was how much we needed to travel along I hat to get to x. So the dot product is telling us about the projection of x onto I hat. Okay, I think that last example merely confused everybody and served nothing. So let's move on, because it actually isn't that important. So, the summary of the dot products. Where have we gone? So, for the dot product, the important things to know are the geometric definition, the numeric definition, and how we write it. That we write it as x prime dot y. A row vector times a column vector. So those are the things that you need to keep in mind. Wow, that's scraggly handwriting. But anyway, as long as it's legible, we're good. So what if you had multiple dot products that you wanted to take? Not just one, but more than one. So for example, let's say that you had two vectors, m1 and m2, and you want to compute the dot product of m1 times x times the dot product of m2 times x. That would give you two different numbers. In linear algebra, when you're dealing with lots of numbers, when you're dealing with many different things, often you package them into vectors or matrices. They're convenient ways to package lists of numbers. Right? So let's package these two into a vector. As usual, our default is going to be a column vector. So this is vector m1 dot x, and the second element of that column vector is going to be m2 dot x. So it's just two separate dot products. Now, notice that m1, because we've taken its transpose, is a row vector, so it lies horizontally. And m2 is also a row vector. It also lies horizontally. We're going to rewrite this like this. Right? We take our m1 vector, and here it is lying horizontally. It's a row vector. We take our m2 vector, and there it is lying horizontally, and we've packaged them now one on top of each other. Now this is a matrix, because it has as many columns as there were elements in m1, and it has two rows. And now we're going to have our vector x. As usual, it's a column vector. And this defines a matrix times a vector. This is another operation that we now have. So if you multiply a matrix times a vector, that's like doing a stack of independent dot products. Sorry, you had a question.
Is that a transpose or a dot?
Sorry, which one? So this one's a transpose, this one's a transpose, this one's a dot, and this one's a dot.
Or when you...
And this is a transpose, and this is a transpose, and I forgot to put the dots here. So that defines, yes?
As a side question I'm having, difficulty conceptualizing what the length of a non-two-dimensional vector would be. Like, it's easy enough to figure out.
Oh, same definition.
Okay.
If you have a 10-dimensional vector and you want to know its length, you square each of the elements, you add them all up, and you take the square root. Same thing, just generalizes to n dimensions. Okay, so this defines how we multiply a matrix times a vector. And we can write that in a number of ways. The important things are, if you have M, a matrix times a vector, you treat each row independently. And you stack them vertically. That's barely readable. So remember when we were talking about the elements, let's say that y is mx. Okay, in other words, let's say that we multiply a matrix times a vector, and the result is a vector. In this case, we're going to call the result, we're going to give it the name y. What we mean by this is that the ith element of y, so that's going to be the result of the ith row of m dot product with x. The ith row of m are all the elements that have I in their row. Remember, we always do rows first, then columns. That's how we were defining matrices. And so this element of the matrix M, that means the ith row, the jth column. And if we multiply that by the jth element of x, and we sum over all of them, that's the numeric definition of a matrix times a vector. And this is exactly the same as you stack the dot products just on top of each other. Right? So what we've written down here is exactly the same as the dot product for row I, for one row, and we're saying that applies to all the rows. You just do them all independently. So
is that a sum of I?
yes, it is a sum over I. You'll have to tell me, later when you're looking at the notes, whether they're readable enough to be useful or whether the handwriting is so illegible that it's not useful. Yeah.
Sorry, what's that with a line after row?
This one right here,
Yeah.
independent. Treat each row independently.
And then it's xj bottom.
And it's xj on the bottom, yes. Oh, now you're right. Well, why? So, what does this mean? What does this definition mean for some matrices? Let's say that we were thinking about 2 by 2 matrices. So let's say that we're thinking about the results being in the vector y1, y2, and we're saying this is going to be the multiplication of these are the various elements of the matrix M times the vector x. So this is how you would see a matrix in Julia, for example. And remember, it goes rows, columns. So first row, first column, second row, first column, and so on and so forth. And if we follow the definition that we wrote in the immediately previous slide, what we're saying is that y1 is m11 times x1 plus m12 times x2. And I wanted to make an animation just like the dot product animation, but now for the matrices, but it was 3 a.m. and I was like, okay, enough. But imagine that we're doing exactly the same thing, right? Imagine that these guys float up to lie horizontally on top of these guys. You do the element by element multiplication. Here's the element by element multiplication. You add them all up. That's the dot product. That's on the first row. And then for the second row, you just repeat. Right? But this time, you're using the second row of n. And all I'm doing is writing out, for this example, the definition of what we had before. So let's look at a particular example. You'll notice that what these are, yes?
Is that percent x2 on the y2?
Oh, thank you very much. This is the next one, and so this is the next one, this is the next one, this is the next two, this is the next two. So here you'll notice that we have two y's, two x's, and a bunch of coefficients here in the m's. Something that you often do with matrices is you want to invert them. What do I mean by that? Imagine that this vector represents the activity of neurons in layer 4 of V1. And these are the weights going from layer 4 to layer 2. And this is the activity of the neurons in layer 2. Say that you know the activity in layer 2 and you know the weights, and you want to ask, what were the inputs? In other words, you want to undo this operation. So let's look at a particular example using exactly the same thing as we had before. Meaning, we said we'd have our vector y1, y2, and this was going to be equal to the matrix n times x. And so this might look something like y1 is 3, and let's say, just to do an example, 3 equals 4 times x1 plus 2 times x2. And let's say that 4 is 7 times x1 plus 3 times x2. So that, what we've got here corresponds to multiplying this matrix times the vector x1 and x2. And what we're saying is, we know the result. It's the vector 3, 4. And we want to find out what x1 and x2 are. Well, we've got two equations. We've got two unknowns. You know that you can do that, right? It's a bit of a pain. Bit of a pain. You got to figure stuff out. And we don't like figuring stuff out. Or maybe you guys do. I don't. I like it when things are easy. So let's look at another example. What if we said the matrix is this matrix, 2, 0, 0, 3. This kind of matrix is a special kind of matrix. It's called a diagonal matrix. Okay. A diagonal matrix has zeros on all its off diagonals. So this is the diagonal axis of the matrix. These are off diagonals. So we've got zeros on all the off diagonals, and that's what makes this a diagonal matrix. And then the kinds of equations that we'd be looking at would be equations like this. 3, 4 is 2 times x1 plus 0 times x2, and the 4 is 0 times x1 plus 3 times x2, which is 2 times x1 and 3 times x2. That's the vector that we're looking at, right? In other words, the equations that we have are 3 is 2x1 and 4 equals 3x2. Can you solve for x1 and x2? Sure, right? Much easier. So what happened? What happened was that the x1s and the x2s weren't mixing with each other. Because all the off diagonals were 0, all those mixing terms were 0. So when a matrix is diagonal, it simplifies our life tremendously, because instead of the different dimensions kind of talking to each other and mixing up, they all separate. And so we end up talking about an independent set of simple scalar equations. No vectors anymore. Each of these equations is just a scalar. So diagonal matrices are very important. And in fact, the big story of what we're going to do over the next 2 or 3 weeks is rewrite matrices so they become diagonal, because then they totally simplify your life. We've got 3 minutes left, but they're going to be a fun 3 minutes, I promise. So bear with me, okay? We're going to use them. Imagine that we're looking at a square matrix, okay? So let's say that M is n by n. Okay? So if you have the same number of rows as you have number of columns, that's what's called a square matrix. And now if we look at this equation, y equals n times x, what this says is, if you give me a point in x, in n-dimensional space, and you multiply it by this matrix M, you get another point in n-dimensional space. In other words, you're transforming space. This is a recipe where it says for any point in space, this is how that point in space, it gets moved to a new point in space. This is what happens to it. And the recipes that matrices define are very special because they're continuous and they're linear. And we'll talk more about that in a second. But the thing I want to leave you guys with is the geometric interpretation of matrices. We got to matrices, and by the time we got to matrices, indices were flying about, and sum over J of Xij and Mij and all this kind of stuff. That's all the numeric stuff, which is fun and is precise and is correct, but to me it's kind of boring. The geometric part is the part that is really interesting. Let's look, for example, at this diagonal matrix, which you guys can't quite see. So let me move this a little bit. Okay. So this is a diagonal matrix, and this is some code that you guys got for the problem set. And let's look at what that matrix does geometrically. So what I'm going to do over here on the plots is sprinkle it with points at random, and then each point I'm going to move to the result of multiplying it times that matrix. That's what that matrix does. That matrix does something to space. It squeezed space horizontally, and it stretched space vertically. Why was that? Because the horizontal dimension we're multiplying by a half, whereas the vertical dimension we're multiplying by 2. So we squeeze horizontally, we stretch vertically. Is that a question? No. And for any matrix, I encourage you guys, when you get this matrix animation thing, to have fun putting in matrices and just seeing what it does. So, and this is the last thing we're going to do. Let's define a few matrices and just see what transformation of space they mean. And once again, we have, here's the numeric representation of this matrix M1, and then what it does to space. That is the geometric interpretation, and there's a one-to-one relationship between the two. So let's take M2 is 1.1, 1.15, 1.65, and you guys are all itching to go, but I'm going to let you go, I promise, I promise. This is the last thing that we're doing, and I hope you guys will do some of this in the problem set. If you do the problem set, this is the fun you're going to have. So let's look at matrix M1. That's the stretching and squeezing that M1 does. Let's look at matrix M2. Did you guys notice anything about those two transformations? Let's look at matrix M3. Does another kind of transformation. Now, each of the transformations that happen, if you change x by a little bit, when you multiply m times x, change x by a little bit, just if you go through the equations, that means that the result also changes by a little bit. So that means that as you do stuff to space, we can't rip it. 2 points that start together, 2 x's that start close to each other, will end close to each other. That means no rips. What we can do, we can stretch, we can rotate, we can squeeze, we can do some shear. Those are the things, the transformations of space that linear algebra allows. And those transformations have some special properties that will allow us to turn any matrix into its diagonal version. 250, it's not even 251, just in time, just in time.